A load is visible from outside, stress is what the material experiences inside, but here is the puzzle. At one tiny point inside a solid, we can draw 9 stress components, yet only 6 independent numbers are required. Why? To answer that, we will cut loaded bodies open, examine normal and shear actions, build the complete three-dimensional stress tensor, and finally connect it to safe engineering design. Consider a body carrying external forces. Imagine cutting it at any location and removing one part. The remaining part can stay in equilibrium only if the removed material is replaced by distributed internal forces acting across the cut. Their intensity may vary from point to point. Over a very small area, the limiting internal force per unit area is called traction. The component perpendicular to the plane is normal stress, and the component lying in the plane is shear stress. Stress is therefore defined at a point and with respect to a selected plane. Its SI unit is the Pascal or Newton per square meter. Engineering stresses are commonly expressed in megapascals. Stress, strain, strength, and pressure are related, but they are not interchangeable. Stress describes internal force intensity, strain describes relative deformation. A constitutive law, such as Hooke's law in the elastic range, connects the two. Stress can arise from applied force, imposed displacement, contact, inertia, or restrained thermal expansion. Strength is a material capacity, such as yield or ultimate strength. Stress is the demand produced by a particular loading and geometry. Pressure in a fluid at rest is a scalar compressive quantity acting normally in every direction. Solid stress is a second-order tensor and can contain both normal and shear components. Normal stress acts perpendicular to the selected cross-section. For a straight prismatic bar carrying a concentric axial force, the average normal stress is sigma equals P divided by A. Pulling produces tensile stress, pushing produces compressive stress. Far from the load introduction, a homogeneous bar with a centroidal force can have an approximately uniform stress distribution. The formula is an average. Near grips, holes, sharp corners, or abrupt changes in area, the local stress is not uniform. If the resultant misses the centroid by an eccentricity E, it also creates a bending moment P times E. The section then carries combined axial and bending stress. Bearing stress is compressive stress produced where two bodies press against each other, for example at a pin, bolt, support, or foundation contact. A simple bearing calculation uses the force divided by a projected contact area. That value is an average design stress, not the true point-by-point contact pressure. The real distribution is affected by curvature, clearance, stiffness, and local deformation. This distinction matters. A modest average value can coexist with a much larger local peak near an edge. The load path must also remain clear because every contact force becomes an internal stress field in the next component. A bending moment curves a beam and creates longitudinal normal stress. Under the usual linear elastic beam assumptions, sigma equals minus my divided by I. Stress varies linearly with distance y from the neutral axis. It is 0 at the neutral axis and reaches its largest magnitude at the extreme fibers. One side is in tension and the other is in compression. Reversing the moment reverses those sides. The second moment of area I measures how the cross-sectional area is distributed about the neutral axis. Placing more material farther from that axis reduces bending stress for the same moment. Shear stress acts tangentially along a plane. Instead of directly changing length, it tends to slide neighboring layers and distort angles. A rectangular element can become a parallelogram. In a simple connection, an average direct shear stress may be written as V divided by A, but that does not imply that every real shear distribution is uniform. On two opposite parallel faces, shear forces must be equal and opposite for force equilibrium, yet those two forces form a couple. Rotational equilibrium requires another equal pair on the perpendicular faces. These are complementary shear stresses. A transverse shear force V in a beam produces a non-uniform shear distribution. For many prismatic beams, it is evaluated with tau equals VQ divided by IT. In a rectangular section, the distribution is parabolic, 0 at the top and bottom free surfaces and maximum at the neutral axis. Torsion creates another important shear field. For a circular shaft, tau equals T rho divided by J. So shear is 0 at the center and increases linearly toward the outside surface. Beam shear and torsional shear have different spatial patterns, but both are tangential components of the same stress concept. Now isolate an infinitesimal cube. Opposite faces carry equal and opposite tractions. Moment equilibrium of an ordinary continuum without concentrated body couples gives three complementary shear equations. First, tau xy equals tau yx. Second, tau yz equals tau zy. Third, tau zx equals tau xz. These equalities are the origin of stress tensor symmetry. We will define the index convention explicitly. The first index gives the force component direction, and the second identifies the normal to the face. A positive shear component acts in a positive coordinate direction on a positive face and reverses on the corresponding negative face. A negative component reverses that complete pattern. At a point, consider the three mutually perpendicular coordinate planes. Each plane carries one normal and two shear components. Arranged systematically, they form the stress tensor. The diagonal entries sigma xx, sigma yy, and sigma zz are normal stresses. The 6 off-diagonal entries are shear components. At first, there are 9 entries. Angular momentum balance makes the tensor symmetric, so each complementary shear pair contains the same value. Only 6 independent components remain, 3 normal stresses and 3 independent shear stresses. A tensor is needed because changing the plane changes the traction even though the material point is the same. When a thin component is loaded mainly in its own plane and out-of-plane stresses are negligible, the state can often be approximated as plane stress. Only sigma x, sigma y and tau xy are independent. This is a modeling assumption, not merely a two-dimensional drawing. For a plane with unit normal n, the traction vector is obtained from Cauchy's relation. T of n equals the stress tensor multiplied by n. Taking the dot product with n gives normal stress on that plane. Subtracting that normal component leaves the in-plane shear vector. This single relation explains why an inclined cut can experience both normal and shear stress. The simple formulas P over A and V over A describe average stress. Real components contain holes, fillets, threads, keyways, and contact edges that disturb the load path. Stress trajectories crowd around such geometric discontinuities, creating stress concentration. The local maximum can be several times the nominal stress even while the total force remains unchanged. This is why a smooth radius is safer than a sharp re-entrant corner, and why failure often begins at a notch. In this lesson, the color field is conceptual. Quantitative design requires a verified analytical solution, experimental measurement, or a properly converged finite element model. Design compares stress demand with an appropriate material resistance. In a basic allowable stress approach, allowable stress equals a selected strength divided by a factor of safety. Yield strength is commonly relevant for ductile materials, while brittle design may use an appropriate ultimate or fracture-based limit depending on the code and failure mode. The factor must cover uncertainty in loading, material properties, dimensions, modeling, and consequences of failure. Margin of safety is allowable stress divided by actual stress minus 1. A positive margin passes the stated criterion. A negative margin does not. Modern design codes may instead use limit states and partial safety factors, so the governing standard always takes priority. We can now resolve the opening puzzle. External loads generate internal tractions across imagined cuts. Each traction separates into normal and shear components. 3 perpendicular planes initially produce 9 tensor entries, but complementary shear equality reduces them to 6 independent values. Axial loading, bearing, bending, transverse shear, and torsion are not separate definitions of stress. They are recognizable patterns within the same tensor description. Geometry decides how the stress is distributed, material strength decides how much can be resisted, and the factor of safety separates resistance from allowable demand. The next step is to rotate the plane and discover principal stresses, maximum shear stress, and the graphical construction known as Mohr circle.